Hi everyone, welcome to this new video. In this video, we're going to learn about time of concentration. So just a quick review of what we've been doing so far. A few videos ago, on video 13, we worked with evaporation. We used the daily pen evaporation. So just to recap really quick, so when it rains, we have water that from all the water that rains, some of it, once it gets to the ground, it evaporates. Then we learn about in video 14 about transpiration, I believe. Yeah, actually, yeah, no, we did the curve number on video 14, which helps us understand how much water is going to get lost with the storage value and how much water is going to run off, right? Then in video 15, we learned about infiltration. So of the water that rains, it either gets evaporated or it can infiltrate into the ground. So we've covered those two parts. Now on this video, video 16, we're going to start learning about what happened to the water that doesn't get lost due to evaporation or infiltration. And one big and important part of that is to find the time of concentration. The time of concentration, pretty much what it is it's the longest travel time it takes a particle of water to reach a discharge point in a watershed. If we have a study area, I have an image here. In this image, what you can say is like how long it takes to the water, to a drop of water, to the farthest uh, drop of water to get to an outlet. And not necessarily the farthest, because at some point we can even have a drop that is here, that is closer to the gauge, to the outlet, but it might take it longer than a drop of water farther on the corner due to its soil type or in land use. It might actually get farther faster to the outlet. So instead of focusing on like the farthest point on the watershed, is actually the longest, the water drop that takes the longest to reach the outlet. So that's like the most basic definition of time of concentration. Now we have a few of equations that we can use to determine the time of concentration. And that's what we're going to learn in this video. This was a pretty long intro, but I just wanted to take the time to pretty much contextualize where we are going and what we have covered so far. So let's start with solving some problems. We have two problems, but every problem has a lot of different parts. It's not complicated. It's mostly just understanding what we are given and applying it on different equations. So let's start with 5.18. Says a watershed with an average slope of 0.00, uh, which is feet over feet, has a land cover of unmowed pasture. The area of the watershed is 2 acres. The watershed drains into an open trapezoidal grassland channel with a base width of 2 feet and side slopes of 4 to 1. Really quick, I have an image of what that could look like. This image doesn't represent exactly those dimensions, but it gives you an idea of what a trapezoidal is. So they gives us the bottom width and the slope of the side walls, 1 to 4 in our case. Let's continue. The farthest point in the watershed is 300 feet from the channel. The channel is 100 feet in length and empties into a wet detention pond. It does give an estimate of the time of concentration of the watershed using the following formulas. We're going to find the time of concentration, or in other words, the longest travel time it takes a particle of water to reach a discharge point in the watershed, using these different equations: the Kirby's equation, Kirpich equation, NRCS, and Bransby Williams equation. Here I have all equations. All you need to do now is just pretty much plug in your values. Remember that for this part, the hardest part is actually understanding the values that they are giving you and assigning them to each variable for each equation. Then it's just plugging and solving for it. So let's start. For the Kirby's equation, we need a C value, L, and S value, so 4 values. The C, we use 0.83 when we're working with feet and 1.44 when we're working with meters. In our case, we're working with feet, so let's use 0.83. Then the length of the flow, we are given the farthest point of the watershed is 300 feet from the channel. In this case, we are assuming that the farthest point is the one that is going to take the longest. Uh, it's not the case every time when you want to be more realistic, but we are simplifying here. Now, n is the retardance roughness coefficient. And we get this value from, if you look in the book, when we cover Kirby's equation, we have this little table, and we are given that our watershed is unmowed pasture, so we can assume that is average grass. It's not dense grass because if it hasn't been mowed, it should be average, like that's what it's normal. So you might want to use 0.4 in this case for n, and the slope is 0.001. 0.001. Okay, so here I already put the equation before I started this video, so I don't lose time typing. But all I'm doing is this equation here with our values, C times LNS here to the negative 0.5, all of this in parentheses to the 0.467. And you should be getting the time of concentration in minutes of about 39 minutes for the Kirby equation. Uh, pay attention to this part here. Usually the Kirby's equation is used with when we have lengths of less than 1,000 feet. And in our case, we have 300 feet of length, so it's appropriate. We're gonna see that in other equations, we are actually not following that. We're just solving it to compare them. Now let's move to the Kirpich equation. This equation only is asking for the length, that is the water is traveling, and the slope. So we know that the slope is 300 feet. Sorry, the length is 300 feet and the slope is 0.001. Again, I already plugged the number, and we got that from 300 feet away, the water is going to take 9 minutes, which is much faster than what we saw for Kirby's equation. And I want to point that out why. And the book mentions, hopefully I found it really quick. For Kirpich, the book mentions that this equation was developed so it can be used for rural areas. This equation is based on data uh, reported by Ramsar for 6 small agricultural watersheds near Jackson, Tennessee. So this equation was developed based on empirical analysis for a specific area. So that's why it's so different in our case from Kirby's. It says that the slope of the watersheds it was tested on was steep, which makes sense. If it's steeper, the water is gonna run faster, right? That's why we get a pretty fast time of concentration. Let's move on to the NRCS method to determine the time of concentration. And the time of concentration is equal to 1.67 the lag time. And so we need to solve for lag time first, which I have the equation here. It's also provided in the book. So to solve for lag time, we're gonna solve for the saturated storage. And to solve for the saturated storage, we're gonna need our curve number. So to use the NRCS equation, we need to start with our curve number. And to determine the curve number, we need to know the type of soil and the land use. We are given that is unmowed pasture, so we can assume it's good pasture, and the type of soil, we're gonna assume that is type C. So using those two values, we can assume that it's open space with good pasture is in good condition, which means that the grass cover is over or higher than 75%. And a type C will give us a curve number of about 74. So using that curve number, we can solve for the saturated storage, which is 1,000 divided by 74, our curve number minus 10. Now we got a saturated storage value. So this value is equal to this. Now that we have the saturated storage value, we We also have that the length is 300 feet. This is feet. And our slope, we need to give it in a percentage, not as a decimal, but so that would be 0.1. And now we have the watershed lag time here, which is about 0.446, and that gives us in hours. So now that we have the lag time value in hours, we just need to solve for the time of concentration, which is going to be 1.67, the lag time. And I have it up here, 1.67, the lag time, and I multiply that by 60 so I can get it in minutes because we're using the lag time in hours. So that should give you about 46, almost 46 minutes. And according to this equation, we get that the time of concentration is 46. So it's higher than whatever we have solved before. What else? Now let's move to the last method, which is the Bransby Williams equation. Now for this equation, we need the length, that is the water is traveling, the area of the watershed, and the slope. Just pay attention that our length is required to be in miles, and our area is required to be in square miles. And our slope can be still the same in decimals, 0.001. So let's do that, 0.001. And then our length, we have it 300 feet. So I already have it solved here to make it into miles. All you need to do is divide by 52 to 5,280. And it's because 1 mile equals 5,280 feet. And very similar to the area, we are given that the area, I believe, is 2 acres. The area of the watershed is 2 acres. So we need to convert those 2 acres to square miles. And 1 square mile is 640 acres. So we just need to do the conversion, which will be the area in acres divided by 640. So now that we have those values in miles and square miles, we can solve for our time of concentration. And all I've done here is plug this equation, and you should be getting about 8.6 minutes. So if you notice here, each equation gives us a very, very different value. And that's because each equation was determined in different areas. Like it depended a lot on the physical aspects and characteristics of the watershed. So when you're in a professional setting, you have to take this into account and see how each equation was developed and see if that represents also the area you are working in. Um, so this is it for this problem. Let's move on to the next one. In this one, we're gonna do very similar. We're gonna take a very similar approach. Just the case it's a little different. 5.19. Imagine a rural area covered in trees and leaves. This area is going to be changed into a neighborhood with houses and lawns. We want to know how long it takes for rainwater to flow from one end of this area to the other, both before and after the change, or before and after the development. So, pre-development, before the houses, we have that the land is covered in trees and leaves, which is ground litter. And then we have that rainwater flows over the ground for 2,500 feet. That's our L, our length, going downhill at a slope of 1%, which is 1 foot down for every feet forward. Um, Post development, after the houses are built, the rainwater first flows over 300 feet of dense grass lawn, and then it flows through a storm drain, a pipe for 1,800 feet. This pipe is designed to move water slowly. What we need to do, the task, calculate how long it takes for rainwater to reach the end of the area in both the before, the pre-development, and after post-development conditions. We'll use different methods to calculate this. With methods that we're going to use for pre-development, we'll use Kirpich's method, NRCS method that we already use, and there is also an NRCS graphic method approach. That is going to be done with the help of figure 5.7 offered in the book, which is this one here. And I have it, apparently we have it twice, so we don't need that one. In post-development, we're going to use Kirby's equation for the first part, for the first 300 feet, And then we're gonna solve for the time of concentration in the pipe for the rest of the 1800 feet. Um, let's start pre-development. Let's solve the time of concentration using the Kirpich equation. Again, the hardest part of this finding time of concentration is assigning the values to our variables. And in our case, we know that is the length, I believe it was 2500 feet. So we have in feet 2500, and that's feet. And the slope is 1%. So in this case, we need to use the decimal approach, 0.01. And solving for the equation, you should get about this pretty much 19 minutes of time of concentration. Using the NRCS equation, again, you need to solve for the lag time first, which will require you to get a curve number to solve for the maximum storage of water or the saturation storage. So given that we're also again gonna assume that is the soil type is type C and we have good pasture. Actually, it mentions wood, I think, in this problem. So in this, I think the problem in the book mentions good wood instead of just trees and leaves. So I didn't adapt that in here, but we might want to use that, and that's why I'm not using table 5.7 as I used before, because this table doesn't cover wood, uh, areas where there is a lot of wood. So we're going to use table 5.8, which is gives us the curve number for hydrologic soil covers complexes. Uh, so in this case, I think let's type good wood, and we're gonna use value of 70. Let me make this bigger. So for type C, good wood, we're gonna use a value of 70. So we plug that in here is equal to 1,000 over 70, which is our curve number, minus 10. And that value is going to be our saturated storage. Our length is the same, 2500. And our slope in percentage is going to be 1%. And with that, we can solve for the lag time. You should be getting 0.88 hours. And again, we want the time of concentration in minutes, so that's going to be 1.67, the lag time in hours, multiplied by 60 to get it in minutes. And you should be getting about 88.44 minutes, or 88 minutes. That's it for this. And now let's solve it. Let's solve the time of concentration using the NRCS method, but the graphic one. And for that, we're going to use figure 5.7. And figure 5.7 requires the type of land that you have and the slope, and that's gonna give you a velocity. Or you can, with this, if you have two of these three values, you can find the other one, right? So we're going to use the forest with heavy ground leader and meadow line here. So according to that, and our slope of 1%, we get, when both lines intersect, we get about 0.25 feet per second, 0.25 of velocity. So now that we determined that, we are going to use, we have the length is 2500 and our velocity is 0.25 feet per second. And then we're going to use time equals length over velocity, which is an adaptation of velocity equals length over time, right? And the reason why we use this equation uh, is because we also could use the Manning's equation, but we are not given information about the channel. Or in the previous problem, we were given the slope one, which I don't know. Yeah, we were given the slope, but we never used it, I think, right? Yeah, we didn't need it. Um, in this problem, we might actually, it would have been nice to have it if we wanted to use it using the Manning's equation, but since we don't have it, we just use this equation here. And having the length and the velocity, we can solve for the time. And this time, and to solve for the time, we do length over velocity, and then we divide it by 60 to convert it from seconds to minutes. And this time represents the time of concentration. So you should be getting about 166 or 67 minutes. Again, it's interesting to see that using the equation and using the graphic equation gives us pretty much double the value. So they are pretty different. And using the Kirpich equation, we have a very, very low value, low time of concentration. So it all depends on the characteristics of the watershed you're working on. Now let's solve for the post-development. Let's see how the time of concentration changes. And for the post-development, we have an part of the travel of the water is on the grass, on the normal surface, and the rest of it is in a channel. So we're gonna have to sum up those two values, and we're gonna get a value here. I have equations already put in here. That's why it says gives us an error. But as we populate the cells, we're gonna get our values. So for the first, I believe for the first 300 feet, we're going to use the Kerby's equation for overland flow through grass. So our length here is 300. We're still using feet, so we got 1.0.83 for the C value. And our retardance roughness coefficient, it says that it's dense grass in our program. Here, dense grass in the post development. So in dense grass, we have a value of 0.8. So we're going to use 0.8 there. And the slope is 1%, so 0.01. So that gives us a time of concentration of 31.45 minutes. That's while it goes over, the water flows overland. Now we need to use the same time equals distance over velocity that we used before um, to solve for the channel. And that's for the same reason. We are not giving information about the channel to use the Manning equation. And that's gonna be the distance. The channel is, it covers 1800 feet. So the channel distance is 1800, and the flow velocity we're given as 3 feet per second. So we plug here 3 feet per second, and all this is doing is distance over time and divided by 60 to convert it from seconds to minutes, and we get 10 minutes. So now we have the time of concentration for the first 300 and for the rest of it in the channel, and we just add them up, and we should get a total of 41.45 minutes for the time of concentration. And let me change the color of the results here. These are the answers for each part of each equation. Um, let's do this and this. And if you notice, we found 41, almost 42 minutes post development. And if you think about it, since we have more area developed, we should have more runoff, or the water should flow faster, which means that maybe here that we got in the pre-development, we got 19 minutes. Maybe the Kirpich equation doesn't make sense because this is faster than post-development. So maybe the Kirpich equation should have not been used for this area at all. These other ones make a little more sense because we expect the time of concentration to be faster um, after the development compared to the pre-development, right? Hopefully, I hope this all is like making sense, and you can now start understanding what we're doing in every single aspect of the hydrologic cycle. In the next video, we're going to start talking more about the duration of the storms and lag time, and I think we're going to start working in with hydrographs. Well, good. This is it for this video, and good luck solving these problems. I'll see you in the next video. Bye.